Thank you for inviting me here. Recall that yesterday, the first talk, Jen mentioned the cost of a tensor, which is measured by rank, border rank, and asymptotic rank. Also, he mentioned the value of tensors, which is measured by subrank, border subrank, and asymptotic border subrank, asymptotic subrank. And here I'm going to give a talk about the value of tensors. In this talk, first I will introduce subranks and border subrank, and then I will talk about the motivation about why we care about subrank and border subrank, and then I will state a main theorem about the dimension of the set of all maximal border subrank tensors, and then sketch the proof of it by using representation theorem and invariance theorem. Okay, so first notations. Let me introduce some notations. A, B, and C here are n-dimensional vector spaces over complex numbers. And AI, BI, CI are denotes the basis of those three vector spaces. And alpha I, beta I, gamma I are the dual basis. And EI is the standard basis of the vector space of dimension S. Here, the unit tensor of size S is denoted the sum of rank 1 tensors, EI tensor, EI in the space CS tensor, CS. And this unit tensor is has cost equal to S, and the value is also equal to S. And a tensor T can be viewed as a linear map from A dual to B tensor C, and similarly we have the linear map TBTC from B dual to A tensor B, and C dual to A tensor B. Okay, and we said that a tensor T is concise if all these three linear maps are injective. And this also means that this tensor cannot be put in a smaller tensor space. And in particular, the unit tensor S is concise in the space CS tensor, CS. Okay, and the maximum possible value of a tensor in A tensor B tensor C is n. The question here we care about is that what other tensors in this tensor space also has a maximum value.
Is concise equivalent to full rank in that partition?
If a tensor is concise, then its minimum border rank is n.
No, just rank. Just wondering what the plain rank in the partition
minimum possible rank is also n. Yeah, and if a tensor is concise. But for subrank and border subrank, all tensor has maximum value.
My question is much more basic. My question is concise equivalent to having maximal rank? Maximal rank of what? In the partition A versus BC, you say, right? And B versus CA and C. I mean, if TA is injective, that's equivalent to having full rank in the partition A versus BC? I think so. Yeah. Okay, so it's equivalent to having full rank in the partition.
Full rank in a slice direction.
Yes.
Yeah. Okay. Any other questions? Okay. Now let me give a definition of those rank notions. Let T be a tensor vector. The rank of T, recall the rank of T is the minimal positive integer R such that T can be written into the sum of rank of R rank 1 tensors, and it is equivalent to say that T lies in this set. This is T can be obtained by applying linear transformations on the unit tensors of size R. Okay. So if R is 1, then that means T can be written as A tensor B tensor C as a single single tensor. Okay. And for border rank of T, recall the definition is that it is the minimal positive integer R such that it is the limit of rank R tensors. So it is equivalent to say that T lies in the closure of the set of tensors that can be obtained by applying linear transformation on the unit tensor R. Okay. Any question about the definition of rank? Okay. Then here the rank give us measures of cost of tensors, and we are wondering what would happen if we switch the position of the tensor T and the unit tensor. So this gives us the definition of subrank. The subrank of T, denoted Q of T, is the maximal positive integer S, such that the size S unit tensor lies can be obtained by applying linear transformations on the tensor T. Okay. And the border subrank of T is the maximal positive integer S, such that the unit size S unit tensor lies in the closure of the set of tensors that can be obtained by applying linear transformations on T. So this subrank and border subrank give us a measure of the value of tensors. And we are most interested in what is the lower bound of rank, border rank, what is the lower bound on cost and the upper bounds on values of tensors. So here I rewrite the definition, and for a tensor T, by definition we have that the subrank is at most border subrank, because here if the unit tensor lies in this set, then it also lies in the closure of it, and also they are both at most equal to n. For subrank, it is at most n by the conciseness of the size of the unit tensor, and for border subrank, it is at most n by the same reason and plus the completeness of the Grassmannian. Okay. And so in this case, so in the case when they are both subrank equal to n, we say that T has maximal subrank, and for border subrank equal to n, we say T is of maximal border subrank. Okay. And also for because this relation is transitive, so border subrank is at most border rank. And so we have this inequalities. Oh, sorry. Okay, and when T is concise, we have that border rank, the minimum possible border rank is n, so we have these inequalities. Okay, so n is the upper bound for the values of tensor, and it is a lower bound for the values of for the cost of a tensor for when the tensor is concise.
Is it obvious that conciseness implies that? Is it obvious that conciseness implies these things?
Implies the least border rank.
Yeah, I guess that's the relevant ones,
right? You gave a proof already before, because border rank bounds the rank of the cut.
Yeah, but it's a cut in two parts, right? So how do I know that it will give me the right properties if I do all three cuts at the same time? That's what I don't. That's what doesn't feel obvious to me, at least. Maybe this one's right. Okay, I'm willing to accept it as obvious, and I won't say it.
Question: is there
yes.
Some intuition about the closure of the space?
It's the Zariski closure.
Zariski closure?
Yes. Here we use Zariski closure.
And home is defined by?
Home is the set of linear maps from A to CS. So if we apply a linear map on T, T is in A tensor B tensor C. So the tensors after applying these linear transformations on T will become a tensor in CS, tensor CS, tensor CS. Yeah. Okay. And we can also define loss rank notions in some higher number of factors, and also in two factors we can also define it. And if we analog the definition to a two-factor tensor, then this subrank and border subrank and they are all equal to the matrix rank. Now let me talk about the motivation from complexity theory. The exponent of matrix multiplication is defined as is denoted by omega, and it is the infinite of real numbers h, such that the rank of the n by n matrix multiplication tensor is equal to big O of n to the omega. Sorry, this is a typo. N to the h plus epsilon. Okay, and this number governs the complexity of all operations of matrix multiplication in linear algebra, and note that this omega is has a lower bound 2, and has a upper bound 3. And in 1969, Strassen proved by using Strassen's algorithm that this omega has an upper bound log with base 2 of 7, which is around 2.81. So this omega is not equal to 3. So the goal now becomes to prove that if omega is equal to 2 or not. Okay. And well-known method to find upper bounds on omega is called the laser method, and it is first introduced by Strassen in 1987. And the idea is to study an intermediate tensor T, which is first of small border rank. That means it has low cost, and second, it is close to being a matrix multiplication tensor. This refers to that this intermediate tensor has high value, and this method is used to prove that omega is less than 2.38, which is a number less than this 2.81. Okay, and so far only 0.004 progress on upper bounds for omega since 1988. So if we want to go further, we need a intermediate tensor that has a low cost and a high value. Here we are interested in the tensors that has large asymptotic subrank, because they are good to get bounds for omega. And a tensor that is of maximal border rank implies that it has maximal asymptotic maximal border subrank implies that it has maximal asymptotic subrank. So here I focus on tensors of maximal border subrank. Okay, and another motivation is from the generic tensors or random tensors. For a generic tensor, the border rank, the rank and border rank of T equal to the maximum border rank, which is around n squared over 3. But for subrank and border subrank, we don't know. It's still unknown. But there is a theorem by Dixon, McCann, and Zuidan that a generic stats lets the generic subrank of tensors in Cn tensor Cn has non-trivial upper bound and lower bounds. And in particular, this means that the generic subrank of a generic tensor is not maximal. And is bounded above by a number around square root of n. We proved a proposition that the border subrank of generic tensors in Cn tensor Cn is at most n-1 for n greater than or equal to 3. So the generic border subrank is also not maximal, but this is the only upper bound that we know for it. Main results that I want to talk about today is a lower bound of the dimension of the set of maximal border subrank tensors. Okay. Now we can view the size n unit tensor being A tensor B tensor C by let it be equal to the sum of AI tensor BI tensor CI as I from 1 to n. We have let the subrank and border subrank of n is equal to n. So the value for this unit tensor is maximal equal to n. Okay, now because a tensor that is of maximal subrank also implies that it has maximal border subrank. So before looking at tensors of maximal border subrank, let's first look at tensors with maximal subrank. The unit tensor has maximal subrank, so its orbit, so tensor lies in its orbit also has maximal subrank. And the proposition, there's a proposition says that actually the orbit of the unit tensor consists of all maximal subrank tensors. Okay, let's prove this. If a tensor is of maximal subrank, then it has subrank equal to n. Then that means there exists linear maps x, y, and z such that the unit tensor can be obtained by applying these linear maps on the tensor T. Then in this case, this unit tensor lies in the image of those linear maps x, y, and z. And since this unit tensor n is concise, so it cannot be put in a smaller tensor space. So this tensor space must be equal to A tensor B tensor C. So this implies that image of the linear map X is equal to A. That means X is invertible and the same as Y and Z. Okay, any questions? Okay. Now let's talk about maximal border subrank tensors. If T is of maximal border subrank, recall that the definition of border subrank is the maximum value S such that the size S unit tensor lies in the closure of the set of tensors obtained by acting linear transformations on T. So when T has maximal border subrank, that means that this maximal size unit tensor lies in the closure of this set. And because we have a closure here, so we can replace those linear maps by using invertible maps. Because we can approach linear maps from by using invertible maps. Okay, so we have this, and now let's define this Q underbar max to be the closure of the set of all tensors that has maximal border subrank. Then since the orbits of the maximal size unit tensor consist of all maximal subrank tensors, so those tensors must be also has maximal border subrank, and so its closure also lies in Q underbar max. Okay. Now let's GB denotes the group G of A equals G of B equals G of C, and here Q underbar max has a lower, the dimension of it has a lower bound by using the closure of the orbits of the unit tensor. So it is equal to the dimension of the group G minus the dimension of the symmetric group of the unit tensor. Here, the symmetric group of the unit tensor is the subgroup of G that fix the unit tensor. And it has a dimension equal to 2n. So the lower bound of the closure of the set of all maximal border subrank tensors is 3n squared minus 2n. This is the first lower bound. And the main theorem that I want to talk about today is that actually this set has a lower bound equal to this number, which is around 2/3n cubed, which is greater than this 3n squared minus 2n. Okay, and the idea to prove this main theorem is that I construct tensors that is of maximal border subrank by using the unit tensor. So if the unit tensor n plus of some, we want to know what vectors when what vectors w when the unit tensor plus w is of maximal border subrank, and let's if we yes.
So can I ask why the dimension of Gn, this the group elements which stabilize n is 2n? What are these group elements which stabilize?
In the next 2 slides, I will have, but it will be on the slides. Okay. So one of its maximal torus is are the diagonal matrices where the product of them is the identity. So that will be the maximal torus of it. Yes. Yeah, so the idea is that we look at the tensors, unit tensor n plus w, where w such that it is still a maximal border subrank tensors, and actually this w lies in a neocomb of the symmetric group with such that it is of maximal border subrank. Okay. Okay, now let's define the neocomb. It is the set of all vectors w such that it is unstable under the action of the symmetric group. That means that 0 lies in the orbit closure of w under the action of the symmetric group of the unit tensor. And let's comb the comb with vertex unit tensor over the neocomb to be the set of tensors v plus w, where v is some scalar times the unit tensor, and the W lies in the neural comb. And we have that the vectors in this form is of maximal border subrank. Okay, then we have that its orbit closure also lies in the set of all maximal border subrank tensors. Okay. Yeah. Okay. This answers your question about the symmetric group of the unit tensor. So it is actually equal to S semi-direct product of Sn and T, where T is a maximal torus, which is tuples of three n by n diagonal matrices, such that the product of them is equal to the identity matrix, and Sn is the symmetric group on n elements. Yeah, and so this T would have dimension to n. Okay. Now we can also define the neural comb by using this maximal torus rather than the whole symmetric group. So we set the neural comb defined by T to be the tensors such that 0 lies in the orbit closure of its under the action of T. And so this is a subset of the neural comb defined by the symmetric group. And by Hilbert-Mumford criterion, note that here we can use this the orbit closure of this comb to estimate the lower bound of the set of all maximal border subrank tensors. But here the neural comb of the symmetric tensor is hard to analyze. So here, so that's why we consider the neural comb defined by the maximal torus. And by Hilbert-Mumford criterion, it says that the neural comb defined by the symmetric group is equal to the symmetric group X on the neural comb by the maximal torus. But since this maximal torus is normal in the symmetric group, so actually we can prove that the neural comb of the symmetric group is equal to the neural comb defined by the maximal torus. Okay. Now let's X ijk to be alpha I tensor beta j tensor gamma k. Note that here alpha I beta j gamma k are the dual bases of bases in A tensor B tensor C. So we can write the coordinate rim of this tensor space to be C to be the algebra C at with variables X I j k. And the neural comb, there is a property of the neural comb that is also equal to the zero set of homogeneous polynomials with positive degree that is invariant under the action of the group. So this neural comb is this, and since the T is a torus and the monomials are the weight vectors of T, so we can just use the monomial polynomials rather than whole homogeneous polynomials satisfying this. Okay. And so since the neural comb now is a zero set of some monomial polynomials, so it is now a union of linear spaces. So by knowing the dimension of those linear spaces, we can estimate the dimension of the neural comb and the cone. And in particular, the neural comb is a subset of this zero set. Here, these monomials are the monomials with degree less than or equal to 3 that's satisfying these properties. And this zero set, because those variables is not repeated, So it is in fact equal to the union of linear spaces with dimension equal to n cubed minus the number of loss monomials, which is this number, where n is by counting this monomial, and n choose 2 is by counting these 3 monomials, and n choose 3 is by counting the number of these monomials.
Excuse me?
Yes.
Why did you choose precisely those monomials? I mean, and why did you stop at that degree? Could you have?
Yeah, because I found this is a union of linear spaces with equal dimensional, which dimension is this, and I found a vector space, a linear space here, and which is also lies in the neural cone. So I guess that implies that for this neural cone, the maximum possible dimension of those linear spaces is equal to this dimension. Yeah. So yeah. And okay. Now so it is this W. I define this W to be the linear span of AI tensor BJ tensor CK, and where at most one of J and K is less than I, and I said, and in fact we can check that this W is one of the linear spaces in this zero set. And in fact, we can prove that this W also lies in the neural cone. So if we have this claim, and that the neural cone is like a subset of the union of linear spaces that with that contains the union of equidimensional linear spaces with one of them is W, then we get that W is a linear space that's of maximum dimension in the neural cone, and so we can use this W to analyze the lower bound of the dimension of the neural cone. Of the neural cone and the cone, and also our main goal, the sets of maximal border subrank tensors. Okay. And let's prove this. To prove this claim, we need to prove that all vector in W is satisfies that the zero lies in the OB closure of it under the action of the symmetric group of the unit tensor. Okay. And now let's this C of T be a curve on the symmetric group of the unit tensor, and it is actually I let this to be lies in the maximal torus, and it is written in this form: the tuples of diagonal matrices with entries T to the lambda I, mu J, and mu K, and here lambda K is equal to lambda K, mu K, and mu K are chosen from these numbers such that it is an element, group of elements in the symmetric group. Then in this case, if we apply this curve on the vector AI tensor BJ tensor CK, we get it is equal to this number T to the 2 to the n minus j plus 2 to the n minus k minus 2 to the n minus I plus 1 times AI tensor BJ tensor CK. So when we choose, if this AI tensor BJ tensor CK lies in W, then that means at least one of JK less than I. Then in this case, when we approach T to 0, we get that this approaches to 0. So vector AI tensor BJ tensor CK in W also lies in the neural cone. This completes the proof of the claim. Any questions? Okay. So now we focus on W rather than the whole neural comb. Okay. Now, so we also consider the comb over W with vertex on the unit tensor. It is defined as the set of all vectors V plus W, where V is some scalar multiple of N and W in little w in W. So it is a subset of the comb over the neural comb of the symmetric group with vertex the unit tensor. So it is also a subset of the set of all maximal border subrank tensors. And the dimension of this comb is equal to the dimension of W plus 1. So this is the dimension of W for n cubed minus 3n squared minus n divided by 6 and plus 1. Okay. And so the OV closure of this cone is also a subset of the set of all maximal border subrank tensors. So by analyzing the dimension of this OV closure, we get the lower bound of the dimension of this set. Now let V be a general point in the comb of in this comb over W with vertex the unit tensor. Where W is any general point in the vector space W. And let this set be a transporter, which is defined as the subset of the group G, such that Gx on this general point V also lies in the comb. Yes. Oh, okay. Okay. The OV closure of this comb now has the dimension equal to dimension of G plus the dimension of the comb minus the dimension of the transporter. Note that we can compute the dimension of the transporter by considering its tangent space. And since its tangent space is the subset of the Lie algebra of G, that's satisfying that when it's applied on the general point, it also lies in the comb, and this is linear space. So and also this condition is some linear equation. So we can use this to get the dimension of the tangent space of the transporter, which is 3n squared plus n plus 2 over 2. Okay. And the dimension of the OV closure becomes to this number dimension of G, which is 3n squared, plus the dimension of the comb, which is dimension of W plus 1, minus the dimension of the transporter. So this is a number it is this number, which is around 2 over 3n cubed. And this gives a lower bound of the dimension of the sets of all maximal border subrank tensors. Okay. Now I want to talk about some future questions about the project of border subrank. So the neural comb, now we know it contains the union of W and its permutations and we have examples showing that the neural comb is larger and actually some not that the neural comb is a union of linear spaces, and we have examples that the sum of the linear spaces has smaller dimension and also some with same dimension, but it's not isomorphic to W. And we are wondering what are all components of the neural comb. And the second question is that a tensor T is of maximal border subrank if the unit tensor lies in the OB closure of T. We are wondering not that if a 0 lies in an OB closure of something, then by Hilbert-Mumford criterion, there's one parameter subgroup of G that can be applied on the T to approach 0. But in this case, it's not. We are wondering if we also have a one parameter subgroup of G that can be X on T to approach the unit tensor. Okay, the third question is that we have that tensors in the OB closure of the cone are of maximal border subrank, but we are wondering, do all maximal border subrank tensors lie in the orbits of the closure of the cone? And do we have this if 2 is true? And so if we have this, then we know what maximal border we know what all maximal border subrank tensors looks like. Okay, and the next question is that this is a new result that by Beggy, me, Jasma, and Rupninsky, that's an upper bound on dimension of the set of all maximal border subrank tensors is equal to n cubed minus n over 3 floor cubed plus 6n squared. And this number is around 26 over 27 n cubed, which is there's a gap between this upper bound and the lower bound that I have 2 over 3 n cubed. So the question is, can we reduce the gap between the upper and the lower bound? And the next question, for generic tensor T, we have non-trivial upper and lower bounds on its subrank, and can we find non-trivial upper or lower bounds on border subrank of a generic tensors? And the next question, the last question, we have method for finding upper bounds for subrank and border subrank of a tensor that rely on other notions of tensor, for example, geometric ranks like rank and G-stable rank. And can we develop a strategy to find the subrank and border subrank that does not rely on those notions of rank? Okay, that's all of my talks. Thank you for listening.